Earth's magnetic field does flip. It has happened many times in the deep past, and there is every reason to think it will happen again someday. But that simple fact is often wrapped in confusion, especially online, where stories about the magnetic pole racing or tipping over can sound like the start of a planetary disaster. The best evidence says something more measured. A future geomagnetic reversal is real as a geological process, but there is no solid evidence that a full reversal is imminent, and if one eventually unfolds, the most likely major consequences would be technological rather than apocalyptic biological collapse. To understand why this subject gets distorted, it helps to separate three things people often blur together. First, there is the geographic North Pole, the point where Earth's rotation axis meets the surface. That does not wander in the way magnetic headlines suggest. Second, there is magnetic north, which is tied to Earth's magnetic field and does move over time. Third, there are the naming conventions of magnetic poles, which can make the language even more confusing. So when a headline says the pole is shifting or flipping, it may be describing ordinary pole drift, not a true global reversal of magnetic polarity. And normal drift is exactly that, normal. Earth's magnetic field is always changing. The magnetic poles move, the field strength varies, and different regions behave differently. A true geomagnetic reversal is something much larger than everyday wandering. It is not a sudden overnight switch where compasses instantly spin around. It would be a prolonged, disorderly reorganization of the entire global field, unfolding over a long period and likely involving a weaker, more complicated magnetic structure along the way. How do we know reversals happened at all? Mostly from the geological record. When lava cools, magnetic minerals can lock in the direction of the surrounding field. Sediments can also preserve magnetic signatures from the time they formed. These rocks act as an archive of past field behavior. That archive is clear on one essential point. Over millions of years, Earth's magnetic field has reversed many times. This is not speculation or a fringe idea. It is one of the established patterns in geophysics. In that chronology, one date matters most for this question. The last full geomagnetic reversal, known as the Brunhes-Matuyama reversal, happened about 780,000 years ago. That number often drives public fascination, because people notice that it was a long time ago and wonder whether we are overdue. But geology is not a timetable with a neat, repeating interval. Reversals have not occurred on a fixed schedule, and the fact that the last one was hundreds of thousands of years ago does not by itself mean another must be close. There is also an important near miss in the record, the Lachamp event, around 41,000 years ago. This was a major disturbance in the field and involved substantial weakening, but it was not a permanent reversal. The field recovered. That matters because it shows that not every dramatic magnetic disruption becomes a full flip. Earth's magnetic behavior includes instability, excursions, and temporary disturbances, as well as full polarity reversals. So, are we heading into one now? The strongest evidence against that claim is straightforward. Institutions such as NASA and the USGS say there is no solid evidence that a full reversal is near. That does not mean impossible, and it does not mean the field is static. It means the current data do not justify saying that a reversal is imminent. Still, several signals are often presented as warning signs. One is the average weakening of the global field since the 19th century. Another is the recent movement of the magnetic North Pole. A third is the South Atlantic anomaly, a region where the field is comparatively weak. These are all real observations, but on their own, they are not enough to predict a reversal. Scientists do not have a simple threshold that says a certain percentage of weakening or a certain speed of pole movement means a flip is about to begin. Part of the reason is that Earth's magnetic field is generated by a geodynamo in the liquid iron-nickel outer core. That system is chaotic, turbulent, and deeply complex. We cannot directly watch the core churning in real time. Instead, scientists reconstruct its behavior from surface measurements, satellite observations, rock records, and numerical models. These are powerful tools, but they are limited tools. They reveal patterns and constraints, not a fully transparent machine with a clear forecast window. That makes prediction intrinsically difficult. If a reversal or a major excursion did begin, the field would likely not simply fade and reappear in the opposite direction as a clean dipole. It could become more complex and asymmetric, perhaps with multiple magnetic centers rather than two clear poles. For everyday life, that would make compass-based navigation less straightforward. For systems that depend on accurate magnetic models, the challenge would be larger. This is where the issue becomes practically serious. The most defensible concern is not that humanity would suddenly be exposed on an unshielded planet, but that a weaker or more disordered field would increase vulnerability to space weather. Charged particles from the sun and energetic events in near-Earth space could have a greater impact on satellites, electronics, radio communication, GPS, power grids, aviation, and radiation exposure during spaceflight. Modern civilization is packed with systems that are sensitive to timing, positioning, and electromagnetic disturbance. The South Atlantic anomaly gives us a real, present-day example of this kind of technical consequence. In that region, weaker magnetic protection allows more energetic particles to interfere with satellites. Operators already know this. Some spacecraft instruments are shut off when passing through the area, or they are monitored more carefully because particle disturbances can trigger errors or damage. That does not mean the anomaly is proof that a reversal is imminent. It means weaker magnetic shielding can have real engineering consequences, even without a global flip. This technological angle matters because earlier reversals happened on a planet with no satellites, no synchronized electrical grids, no precision navigation networks, no crewed spaceflight, and no supply chains dependent on exact timing. In other words, the geological record tells us reversals are survivable for life on Earth, but it does not tell us they would be trivial for a modern technological civilization. Our vulnerability is mainly infrastructural. What about biological effects? Here, the responsible answer is more cautious than many dramatic claims. Earth's atmosphere remains the primary radiation shield, so even if the magnetic field weakened substantially, that would not automatically make Earth uninhabitable. The atmosphere does a great deal of protective work that sensational accounts tend to ignore. There is also no solid evidence that past geomagnetic reversals directly caused mass extinctions. Simple claims that reversal equals extinction are not scientifically established. That does not prove there would be no biological consequences at all. It means the strongest catastrophic version of the story is not supported by the evidence. Animal impacts remain an open question. Many species appear to use magnetic orientation, but often alongside other cues such as sunlight, stars, smell, landmarks, or ocean conditions. Some animals might adapt better than others, especially because reversals unfold slowly on human timescales rather than as an instant event. But slow does not necessarily mean harmless in ecological terms. Changes spread over long periods can still create stress, confusion, or selection pressure. The uncertainty here is real, and it should be presented as uncertainty, not inflated into certainty in either direction. That balance is the key to this whole topic. The magnetic field is changing, as it always has. The rock record clearly shows many past reversals. The last full one was about 780,000 years ago, and the Lachamp event shows that major disturbances do not always become permanent flips. The field today does show features people find alarming, including long-term weakening, pole movement, and the South Atlantic anomaly. But scientists do not currently have robust evidence that these observations mean a full reversal is imminent. The geodynamo is chaotic, and our tools, while powerful, cannot turn that complexity into a precise schedule. So the most defensible middle ground is this. Geomagnetic reversal is geologically normal, biologically probably not apocalyptic, technologically potentially serious, and not currently supported by robust evidence as imminent. If you want more careful deep dives like this, subscribe, enable notifications, and suggest the next topic in the comments.